Hey guys, can you hear me okay? I think so, great. Thanks Phil for the introduction and thanks for having me. Today I would like to talk about text extraction. And basically this talk is about one particular issue and how we solved it using machine learning. We have many related issues. I'm going to get to that at a later point. First of all, short introduction to what GumGum is doing. So GumGum is in the online advertising industry, which means that we sit between the website owners, we call them publisher, and they would like to make money by showing ads. And on the other hand, you have the advertisers, and they would like to show their ads, ideally to the right customer. So what GumGum does is it's trying to optimize that match between the ad and the user and the website. So the context where it all happens is the actual website. So that's why it's very important to see and to know what is on that website in terms of text and in terms of images. So we have two different teams. One of them does computer vision, which is not my team. And we have the other team that does natural language processing. And here are just a couple of examples what we do, for example. So we take the images for CV, and we do image recognition, and we also go in a bit more and say, let's say we have a shampoo ad, then we see, is there a person, what's the hair color, things like that, so different features. And then we decide whether to show the ad. And for natural language processing, we do a whole host of different tasks. You can see like in the center, that long cluster there, what we do is we find good keywords. And by good keywords, it means keywords that represent what's on the page, what's the topic, because a lot of advertising is based on a keyword basis. So the advertiser says, show my ad if the keywords are cars or sports car or Tesla. Right? We do classification, and there's an industry standard called IAB, and it's roughly 390 different categories. So the question is, for each particular website, which topics does it talk about? So we do IAB classification. We do threat classification, which is very important. Let's say BMW wants to show an ad. They definitely don't want to show it if it's an article about a car crash, right? Or about something that's like negative in general. We check out events, sentiment analysis, named entity recognition, auto detection, because we have a lot of customers from the automobile industry. And then for Japanese, because it's a different type of language, we treat it differently for IAB and threat classification. So all of those things we do, but we can't do them if we don't get the first part right. And the first part is we get the page and we need to know what is the good text. Because we can't classify a website if we look at all the text on the page. There's going to be ads, there's going to be links to other articles, there are going to be comments. We don't care about comments. So we only want to have the actual text that is like the article, for example, right? Now, so everything depends on good text extraction. It's a small step, but it's the garbage in, garbage out principle. If you don't get that one right, all of the other ones are going to fail. The problem is that good text extraction is very difficult. One reason is that there are a lot of different layouts of websites. So you can have chats, you can have question pages, you can have blogs, you can have news sites. Sometimes, or quite very often, you have just one image and a caption, and there's nothing. Sometimes you have the main text in the top right corner. Sometimes very often in the lower part. So there's a lot of variation. Many layouts, multiple languages, and a lot of unwanted text, as I mentioned before. So one solution would be to do manual text extraction, but that doesn't scale. So GumGum, and we're not like a huge company, but we do process 100 million documents a month. So doing that, we do have manual text extraction. We have annotators in-house, and we have third-party companies that we work with. And the price for text extraction is roughly 20 cents per page. So if you do 100 million times 20 cents, that's a lot of money every month, right? So it doesn't scale. And what are you going to do when you have new publishers? What are you going to do when a publisher, so a website owner, decides to change the layout? So lots of headache. So the idea is use machine learning to somehow find data, find good features, train your algorithm, and do it in a continuous cycle so that you capture any changes that may happen. And that's basically what this talk is going to be about. So the solution is sort of, we want to have text extraction logic that works well, right? At least as well as human annotators. Because one issue with human annotation is also, it's quite often faulty, especially with text extraction. Like it happens very often if you have a long article, for example, that the annotators just highlight the first 2 paragraphs and then they're done for some reason, right? Or I mentioned the little text in the top right corner sometimes of a website. That is not being detected because that particular annotator thought, well, maybe this is actually not the text, right? So it's not like human annotation is perfect. It's not, right? It's around an F-score of 0.8 or accuracy of around 80% if you want. So what we did is look for a third party that can supply us with data. And that's and one solution that we found, they're called Ifbots. So you can go and check them out. Ifbots is a very cool product, actually. And what they do is you send them a URL, and on the left-hand side, you can see they return to you the extracted text. That's in the lower part there. And a bit of meta information. I think this thing is falling off. All right. They do it in a very inspired way by actually doing an image analysis. So they take an image off the website, and then they have CV to classify what is text and what is not text. They also don't always get it right. They have roughly a 0.9 accuracy, which is very good, better than humans. So that's great. So we could just use that and be done with it. The problem is scaling. This term, it's the price. So if you go to their pricing page, you can do 250,000 pages, get them processed for $300. That's great. But if you want to do 100 million, you're at like a lot of money again. You're like looking at tens of thousands of dollars every month, which is okay. But why not see if you can find a better solution that works equally well? So what we do is, for each of our publishers, for each of our websites, every day we check our logs and we see which were like the most prominent publishers, which website popped up the most often. And then we take them, we send them, we ship them over to Ifbots, and we get back 300 documents. So we pick 300 documents and we get them annotated. We're using 300 because we ran some tests, and after 300, the change in performance is minor. So there's no need to send them 1,000. And then we store that information. And now we have a data set for each website that is working reasonably well. Now, it won't be perfect. And for that reason, we also have our manual annotators. But those manual annotators now only have to contribute a rather small part of the corpus, let's say 20 to 30 pages. We're combining those, and then we're using an available solution called Dragnet, which allows you to do machine learning for text extraction. The great thing about Dragnet is that you can choose your own, it's Python-based, and you can choose your own machine learning algorithm. So we basically went ahead and tested out a couple of possible algorithms. You can see here on the screen in the top left corner, you see a bit of like how features are being handled. So usual features are, for example, the density of text. And you can see in the top left corner, like red is content, blue is non-content. You can see that content tends to be more dense than non-content. It's also looking at HTML tags and CSS features in order to use that as its feature base. In the lower right corner, you can see its performance. So performance is pretty okay. F1 score of maybe 0.83, which is a pretty good result. So next up, the question was, which algorithm are we going to use? And here you can say a bunch of algorithms and their pros and cons, their strengths and weaknesses. What we were looking for is something that an algorithm that can handle high variability, but is easy to train, meaning fast to train, so not as costly as, let's say, for example, a neural network. So yes, neural networks would work, but sometimes it's just overkill. And in this case, it definitely is. So decision trees, I think most of us know them. They're interesting, but they're not very powerful, right? Because they're one set of rules that are basically set in stone, and they lack in tolerance, and they have an affinity for local maxima, which we don't like as data scientists. SVMs, on the other hand, are more flexible, less prone to finding local maxima, but they're pretty expensive to train. So what we ended up with using, and of course we tried them all, so this is more like in hindsight, what we ended using is a random forest algorithm. So random forest, or the extra tree, which is just a variation of the random forest algorithm, is basically an ensemble learning algorithm. So it takes many different decision trees, and then it queries them and asks by, for example, majority voting, this decision tree says this block of text is content, the other one doesn't say it, and so on and so on, and then you basically take the average of those, and that is your answer. So it's a binary classification task for each block of content. Question is it the good text or is it not the good text? And in the background, there are a few other things happening. So random forest also does bagging, so bootstrapping aggregation, which is kind of what I just described. It's using sampling of features, random sampling, and that makes it more robust. So basically, by introducing this element of surprise, of chance, and you have enough of those trees that you query, you actually do in the end very often get like a good result, a robust good result. In terms of features, I already mentioned a few of those. So yeah, we have text density, the link density, we have semantic features from the ID and class tags, and so on and so on. At this point, we're not using any actual text, right? So we're not actually using any words that are on the website. I'll get to that later. And on the right-hand side, you can now see our process of what we do. So basically, every day, for each website, we retrain our algorithm. And we do that because a publisher, a website owner, may decide, hey, I'm going to try like a different layout of my website, right? So we want to catch that as soon as possible, as quickly as possible. And the data set that we use is like a moving window. So we basically ignore data. If we have enough data, then we ignore data that's like a month old, 2 months old. And that allows us to be pretty much like up to speed on like the most recent designs that that particular website is using. The performance that we're getting is pretty good. You can see the F-score compared to our manual gold standard is 0.85. And on the right-hand side, compared to our previous solution, it was something called a boiler pipe. It's doing much better, especially in terms of the cost of deletes. So this is a Levenstein cost calculation, right? So what is the cost of having one character, having to delete one character, right? So the insert, the first one, is the one where Dragnet really shines. So we're getting all of the text usually. We have a higher cost of delete, which means we're getting too much text, right? So that's something that we have to work on. One aspect of it is, and I'm actually quite happy with that, is that in most cases, these are actually image captions. So if you have an image embedded in text and you have an image caption, in theory, that's not part of the text, that's part of the image, right? But Dragnet is still capturing it. And we're fine with that because there's like a gray area. Is it part of the text or not? So, and in total, it's performing much better than before. So are we done at this point? Probably not. From a pragmatic point of view, probably yes, because we have other things that we need to work on, and this works reasonably well. But we will definitely have to get back to improving a couple of things. One of them being trying out more features. So I mentioned that we're not using any language text from the websites. It is definitely an acceptable approach to use stopwords. So for each block of text, how many stop words are there? Or what's the stop word ratio? Stop words, for those that are not NLP people, are functional words. So for the English language, it would be the, for, a, and they are doing a very good job at describing what language a text is in. So a lot of language detection is based on stop word analysis. And we could use that as well. There's an extra tool that's called readability. We may integrate that into our machine learning system. Yeah, and that's basically it. In terms of languages that are not supported yet, so GumGum is working with roughly 14 languages, and some of them are not supported by the official version of Dragnet. So we're basically going to end up contributing back to that open source activity and adding those languages ourselves, making it available then. And that's basically it. Thank you.